within the frame of the activities carried on in OGC Testbed-16, and more precisely in D133 Machine Learning Environment 2 deliverable, we explored how to leverage machine learning technologies in dynamic contexts like wildland fire planning and response, exploiting the use of OGC standards. The aim of the D133 deliverable was to provide a common framework for supporting machine learning applications by defining a standardized way to discover, deploy and run ML models on cloud platforms by means of AIDS interface, defining a standardized way, both data and infrastructures, to discover, expose, use and reuse ML training datasets aimed to interoperability exploiting OGC standards such as the OGC API records for instance, providing model results in a standardized way exploiting the power of map markup language MapML. The AIDS service is the entry point of the framework exposing an OGC standard interface aimed to browse, deploy and run services. The coordinator is the main component in charge of orchestrating the workflow within the framework, calling all the other components and dealing with two distinct scenarios: O training of a machine learning model, O run inference on pre-trained machine learning model. The dataset loader is responsible to discover and collect data using OGC standards and other third-party protocols. The input adapter is in charge of manipulating data retrieved by dataset loader, converting it for specific machine learning model contained in the environment. The machine learning model is itself the core element of the framework. The framework has been equipped with just one demo model aimed to predict fuel loads from Sentinel-1 data and is encapsulated in a Docker container for quick and easy deployment mainly but not only into cloud environments. Symmetrically to the input adapter, the output adapter is in charge of adapting model result in order to be correctly processed and published by Geoserver. The model results are exposed by a Geoserver to relevant MapML clients using an OGC Web Map Service Standard implementation. This was the overview of the main components composing the machine learning environment. Now let's see in more details how each component works. All the requests for the discovery, deployment and running of a machine learning model are made through a dedicated AIDS service exposed. The AIDS server is based on a Crimweaver implementation starting from original Docker image. For this deliverable, only two different types of services have been registered in the AIDS: model training and model inferencing. Beside these, the AIDS service exposes standard calls such as the get capabilities and describe process to discover and browse available services. In order to trigger either the model training or the model inference, specific WPS execute services are made available, each one with specific parameters like, for instance, the endpoint and catalog name of the server hosting input data, type of protocol for accessing data or the checkpoint to be used. If the request is accepted and queued correctly, the client is provided with the job uniquely identifying the request and needed to query the status of the request. The coordinator acts as a process dispatcher and orchestrator between the components of the ML environment framework in order to execute two typical services of the architecture: train a model or trigger model inferences. It is called by the AIDS interface using parameters coming from the WPS call in the CWL. As a first step, the coordinator invokes the dataset loader to retrieve the data using the parameters in the request, that is either to retrieve pairs of input and ground truth data or just test data to run ML model inference on. When data is available, the coordinator invokes the input adapter to manipulate, if necessary, data to cope with ML model input data requirements. At this stage, data is ready to be used by the ML model. If the training service has been requested, the coordinator calls the ML model to train on input and ground truth data, either resuming from an existing checkpoint or starting from scratch. Instead, if it is triggered by the inference service, the coordinator issues the loading of the ML model checkpoint file and runs inference on input data. When inference is completed, the output adapter is called by the coordinator to handle the results from the ML model be converted and published on the Geoserver to allow MapML clients to access the generated output. The dataset loader was designed to generalize access to data and to enable handling data coming from providers exposing different protocols and standards, such as OGC CSW, WCS, WMS, Google or Amazon buckets and so on. The data loader component performs a set of actions that can be grouped into two different stages: a metadata discovery stage to retrieve the metadata associated to the queried resources, and a resource download stage, where the resource is downloaded using different protocol, like CSW, WMS or WCS, based on the information contained in the metadata. One of the most critical aspects of the framework design concerns how to cope with different and extremely specific ways that each ML model handles input and output data. The role of both input and output adapter is to provide a bridge between framework internal flows and the model itself, thus providing system modularity. The input adapter deals with data retrieved by the dataset loader that needs to be converted and formatted as required by specific ML model. Moreover, the data downloaded might be not usable as is, requiring some pre-processing activities, such as data calibration, orthorectification and so on. The output adapter, instead, acts in a symmetrical way, taking the results coming from the ML model, converting the data, and pushing it to the Geoserver via a dedicated REST interface. In this context, the input adapter has been customized to orthorectify Sentinel-1 data loaded, to convert the values in a logarithmic scale via a dedicated snap workflow, and to resample the result to match the spatial resolution from original 10 meters to 30 meters of the ground truth data. The default AI model delivered within the environment is a deep neural network based on U-Net architecture. The network takes as input a GeoTIFF image containing the VV polarization channel of Sentinel-1 and predicts, as single-channel GeoTIFF image, the total biomass, where higher concentration of total biomass is associated to higher pixel value in the image. The predicted total biomass image coming from the model is then converted to a green shade image. The Geoserver is the last step of the ML framework chain, and its role is to make publicly available the results of the ML model inference in MapML format and via a WMS interface. In order to activate support for MapML, a dedicated module has been installed into the bare-bone Geoserver delivery. The use of MapML has already been exploited in previous OGC testbed initiatives like OGC Testbed-13, 14 and 15. The MapML modules include support for styles, tiling, querying, shading, and dimensions options for WMS layers, and also provides a MapML output format for WMS get feature info. An example can be found at following link. The publication of the image is done by means of the Geoserver REST API. Two steps are necessary in order to expose the image: create a data store with a URI link to the image to make the image recognized by the Geoserver. Create a layer to make the image available to users. As an example, the following figure shows the rendering on MapML internal client of the Geoserver. Several interesting outcomes come with this activity. It has been implemented a framework that can be used as a skeleton for theoretically any machine learning model, thanks to input-output adapters, and virtually coping with tons of different heterogeneous data sources. The modularity of this framework also permits any extension on any step of the whole chain. For instance, it would be possible to change to final output just simply swapping the MapML with a different standard and only updating the relevant output adapter, maintaining the rest of the structure as is with no impact and side effects. As already highlighted in Testbed-15, speaking merely about development, having plenty of Python libraries available that implement OGC standards is really useful. Also, the AIDS WPS server already available, it has been a valuable benefit. Having the framework encapsulated in a Docker container helped a lot to test the whole application independently for the environment and to scale it in production. The use of the Draft OGC API record standard eased the development and the querying mechanism having to deal with a single standard. For sure, some additional improvements are needed, e.g. some specific identifiers to find exactly the resource and format needed. At the same time, it is really simple to integrate within the framework other catalogs served, for instance by OGC CSW standard and data providers exposing OGC WCS services for the data retrieval. In addition, just upgrading the data loader component, it would be possible to integrate additional repository like Amazon S3 Google Cloud Storage. In conclusion, it has been demonstrated not only the feasibility of a machine learning framework environment in a generic and complex context, but also all the potentiality coming with this approach in terms of modularity and expandability.